Okay, today we're going to talk about how we can graph quadratic equations. And it covers the integrated algebra standards AA41, which is determine the vertex and the axis of symmetry of a parabola, and AG4, which is identify and graph linear and quadratic equations. And we've already done the linear part. So for our vocabulary today are roots, vertex, and line of symmetry. So the first thing I want to cover is how a quadratic equation is different from a quadratic function. These two things are different because a quadratic equation is just one example of something that we would consider a quadratic function. So first, if you think about the structure of these equations, or these two mathematical objects, we have on the left-hand side the same expression. We have x squared minus 4x plus 1. But in the quadratic equation, on the right-hand side, we have a constant. And in the quadratic function, on the right-hand side, we have another variable. So a quadratic equation is one specific instance of a quadratic function. It's the function when it's equal to one certain value. So when we have a quadratic equation, we can solve it like we did in the last lesson. The purpose of an equation is to find out what x could be for a specific value of y. In this case, the y is equal to 0. But a quadratic function is, it marks the way that the expression changes with certain values of x. So here, this is many different, I'm supposed to be putting in many different values of x, and I'm trying to figure out how y changes when I change the values of x. So the function has an infinite amount of solutions to it, whereas the equation only has, in this situation, this equation only has 2 solutions to it. Okay. So we're going to be graphing functions today, and I actually should have used the word function here. So how do we graph a quadratic function? Well, the first thing is, and I want to use a table of values to graph. That's going to be the first way I'm going to show you how to do this. Now, I want to look at the values of x between -1 and 5, including the values of -1 and 5. We say that's inclusive. So I put the value of x's on all the integer values of x between -1 and 5 on the left-hand column here. And I'm going to substitute these values in the equation. So it's -1 quantity squared minus 4 times -1 plus 1 for the first one. So -1 squared is 1. And then you'd have plus 4 because minus, you'd have, actually what you'd have is minus a -4. So if I were really doing this out all the way, we have minus a -4, and then we have plus 1. Well, that would be 1 plus 4 plus 1, so the answer here would be 6. Okay, now I put in -1 and I got back 6. Okay, similarly, if I put in 0, what I'm going to end up getting back is actually 1 because these two terms knock out. So 0, 1 is a graph. I'm going to go ahead and pause the video and fill in the rest of the table here, and you can do the same with yours. Okay, so I went ahead and filled in the table, and I also plotted the points on the graph to the right. Now, as you can see, we have -1, 6. We have 0, 1, 1, -2, 2, -3. So in all of these, the line appears to be going down until it gets to a certain point, and then what you'd see is it appears to be going up in the same manner in which it went down. So it appears to be symmetric about this certain point. So the right branch as it goes up is the same way that the left branch was as it went down, and you can see that in the coordinates. So it goes for 1 it goes -2, then -3, then -2 again, and then 1, and then 6. So you can see 6, 1, -2, -3, -2, 1, 6. All right, as I increase the values of x by 1 every time, the y values appear to go down and then come back up. Okay, and that's the feature of a parabola. So this right here is the graph of the equation y is equal to x squared minus 4x plus 1. Now, the point that we just saw, so I've just flipped to another page where this is already graphed for me, this point right here is a special point called the vertex. And for our graph that we just plotted, it's the minimum value of the graph. It's the smallest point where the y can be. So the graph goes down and it starts bouncing back up, and that's what makes it the form of a parabola. Okay, that's one of the characteristics of a parabola. It goes down, and it starts bouncing back up, or other parabolas can go up and start going back down again. Now, the formula, it actually, the vertex has a special formula to it, and let's look back at the coordinates of the vertex here. The coordinates were 2, -3. And so there's a formula, and there's also, through the vertex, if I drew a vertical line, this line would be, the graph would be symmetric about this vertical line. So this left-hand branch, if you folded it over, it would be go right on top of the right-hand branch there. Now, the equation of this line of symmetry has to do with, I can get the x value for the line of symmetry, or actually the equation for the line of symmetry, or the x coordinate of the vertex, because remember, this is the vertex right here, so it has an x and a y coordinate. Now, the x coordinate of the vertex is also like the x value from which we would make the equation for the line of symmetry. Remember, vertical lines have like the equations that are x is equal to something. So the formula to find this particular x value, or this equation, can be derived from the quadratic equation, or the quadratic function written in standard form. All right, so the function in standard form is y equals some coefficient times x squared plus some coefficient times x plus a constant c. So let's look at our equation here. We have y equals x squared minus 4x plus 1. Now I'm going to rewrite it so that it's in the form of this, in standard form. So y equals 1x squared plus -4x plus 1. So a would be equal to 1 in this case, b is -4, and c is 1. And it turns out that if I take these a and b values and I put it into this equation here, x is equal to -b, so it means take the opposite of what b is, over 2 times a. I'd have x is equal to the opposite of -4 is 4 over 2, x is equal to 2. And notice that was what our x and y coordinate, or that was what our x coordinate was. It was 2, -3. Okay, now in order to get the y coordinate of 3, I'd have to put the x coordinate back into the equation. So I'd have y is equal to 1 times 2 squared plus -4 times 2 plus 1. I'm just putting 2 back in. And if I did this, I'd have 4 plus -8 plus 1. That would be -4 plus 1 is -3. And so that verifies what we found here, which is that the coordinates were 2, -3. Okay, so in order to find the coordinates or the line of symmetry now would be y is equal to 2. And remember, when we graphed all those vertical lines, we'd said that x is equal to some constant was a vertical line. All right, so we're going to use that information in the following pages to find out other ways to graph the equation. Now, let's look at a table where the leading coefficient is not positive. So this equation right here, y is equal to, now remember that negative in front of the x squared is like -1x squared minus 2x plus 5. And I'm going to look at it for values of x ranging from -1 to 5 as integers. Okay, so let's start putting these values in. Now remember, if I put -1 in, I have -1 times -1 squared minus 2 times -1 plus 5. So -1 squared, by the way, is -1 times -1, so that's 1. But then when I multiply it by another -1, that whole thing ends up being -1. So, and this would end up being plus 2 plus 5. So my coordinate pair is, I put -1 in here for x, and I got back, let's see, this right here is 1, positive 1 plus 5 is 6. Okay. All right, let's try another one here. Let's try to put in 0. So I have -1 times 0 squared minus 2 times 0 plus 5. Well, these two terms knock out, so I just have 0, 5 as my term. Let's try to put 1 in. Negative 1 times 1 squared minus 2 times 1 plus 5. Well, the first thing is going to be 1 squared is 1 times negative 1 is negative 1 minus 2 plus 5. This right here is going to be negative 3 plus 5, which would end up being positive 2. So I have 1, 2. Now I'm going to pause the video and fill in the rest of this table. Okay, so I filled in the table up to 4, and I plotted the points. And what I want you to notice is it looks like if I connect these points, I plotted some of the points. I plotted this point, this point, this point, and this point. And I want you to start noticing that it looks like the graph is curving upward. So what I want to do is I want to use the vertex information. So remember, the vertex calculation is negative b over 2a. So our b here is negative 2 and our a is negative 1. So this will be the opposite of b, which is 2 then, because b is negative 2, over 2 times negative 1. So that's 2 over negative 2, which is negative 1. So our vertex is at negative 1. So this point right here, this green point, is our vertex. That means that the line is going to be symmetric about those points. So what I'm going to do is, because what starts happening is it starts getting much more negative fast, or it gets negative faster and faster as I increase my x values. And it's really difficult. I don't have a graph that goes down that far, but since I know the vertex is also the line of symmetry, I'm going to draw this line of symmetry, and I'm going to take my points. So if it went to negative 1, 6, and the next point was 0, 5, then I have a point on the other side. I'm just going to reflect this point right here on the other side of the graph in order to use the line of symmetry to fill out the rest of the graph. So if this next point were 1, 2 right here, then I'm going to go, that was 2 points away from the line of symmetry. I'm going to go 2 points on the other side. Okay, so there's that point. 2, negative 3, so that's 2, and that was negative 3 right here. So that's 1, 2, 3 points away. So I'm going to go 1, 2, 3 points on the other side. Okay, and 3, negative 10, so 3 is 1, 2, is 1, 2, 3, 4 away. So I'm going to go 1, 2, 3, 4 away on the other side. And that completes the drawing of my graph right there. So what you notice is that when the a value is negative, the graph ends up being pointed downward. All right, so I used a lot of different strategies here. I used the strategy of finding the vertex, then I found the line of symmetry, then all the work that I had done to get these points, I didn't have to redo in order to get the points on the left-hand side of the parabola, because I could just use my line of symmetry and my understanding of reflection to fill in the rest of the graph. So there's two cases here. When the leading coefficient, or the coefficient of the x squared term, is greater than 0, the parabola is pointing upwards. Sometimes people say that it's smiling. And then the vertex becomes the minimum point. But when the coefficient of the x squared term is negative, it's like a frown, right? It's like pointed upside down. And this vertex becomes the maximum. So we saw that in this case. The vertex here, the line of symmetry was x is equal to negative 1, and that vertex was negative 1, 6, and that was a maximum point. It was the highest y value that this graph had achieved. The highest y value that it would have achieved is positive 6. Okay, and the other thing I want to show you in this video is how to find the roots. Now the roots are what we call the x-intercepts. So we can use the finding of these roots in order to be able to graph them more efficiently. So the roots, to find the roots of any graph, you just have to find the x-intercepts. So it's where the roots are where the graph passes the x-axis. So here there's 3 different cases. There can be the quadratic equation can pass the x-axis twice, in which case there are 2 distinct roots. It can go down and bounce on the x-axis, so there's only, it actually, what ends up happening here is this is one repeated root, like we talked about in the lesson before. Or the parabola can actually not pass the graph at all, in which case there are no real number roots. When you get to algebra 2, you're going to figure out that there are roots to this quadratic equation right here, but they're going to be imaginary numbers or complex numbers is another way of, well, a complex number has an imaginary number in it. So there are no real number roots to this. When it looks like this, there's no real number roots, but you'll find complex number roots when you're in algebra 2. So how do we find these x-intercepts here? Well, it's pretty easy. We set, remember, the x-intercept is the y value, or it's the x value when the y value is 0. So we go ahead and set these equal to 0. Okay. Now we learned in the lesson before how to use the x factor to factor this. So, whoops, I should have had the -7 up here and 10 here, so that's going to be -5 and -2, so x minus 5 and x minus 2. Now we have two different cases, right? So we want to set up two equations, this one and x minus 2 equals 0. So we'd have here x is equal to 5 and x is equal to 2. Now if we look here, that's exactly where the roots are. X is equal to 5 and x is equal to 2. So we're using the information from the quadratic equation, from finding the solutions to a quadratic equation to finding the roots to a quadratic function. Okay, that's why we learn how to do that. So let's go backwards now. If I gave you a graph and in order to find the roots of the graph, I could just look, or in order to find the equation of the line, I can just look at the roots right here. So this right here is x is equal to 1, and this right here is 1, 2, 3, 4, so x is equal to -4. Then my quadratic equation, working backwards, it came from x. So I knew the solutions were x is equal to -4 and x is equal to 1. So here I must have had x minus 1 and x plus 4 equal to 0 for my individual equation. Okay, now if I FOILed this out, I'd have x squared plus 4x minus 1x minus 4 equals 0. So this would be x squared plus 3x minus 4 equals 0. So my quadratic function is x squared plus 3x minus 4 equals y. Okay, now look again, this is what I did. I went backwards. So I was given the two solutions. From there I made the two binomial factors. I FOILed them out to get the quadratic equation, and then instead of putting 0 on one side, I put y on one side in order to get the quadratic function. So this is the equation for this line. I found the equation using the roots. Okay. So we want to, if we wanted to graph the quadratic function that we have here, the first thing that we want to do is we want to find the roots of the quadratic function using what we just learned, find the vertex, and plot 3 points in graph. So if we find the roots, the first thing we do is we set this equal to 0. Okay. Then we use the x factor to find the binomial factors. Now, just by inspection, I can say, well, the x values are going to be -2 and -3 here. If I made those two specific equations, x plus 2 equals 0 and x plus 3 equals 0. So those are the roots. So that tells me where the graph passes the x-intercepts, or the x-axis. So let's plot x equal to -2 and x equal to -3. So actually, this graph is going to go up pretty fast, or it's going to go down and dip somewhere between these two roots. Since the leading coefficient is positive, it means it's going to look like this and not like this. So if we found the vertex is x is equal to -b over 2a, where -b would be -5 over 2 times, now 1 is the leading coefficient, so it would be -5 over 2, which is -2.5. Now if we zoomed in on this graph, we could see that that's right in between our two roots. So negative 2.5, it's going to go down somewhere over here. Now to find the y value, let's put the x value back into the equation here and find the y value. Okay, so I went ahead and did that up here. Whoops. And I found that when the x value is negative 2.5, the y value is negative 12.25. So it's almost like off my graph here. It would be somewhere down here. So the graph looks like it's pointing upward. Whoops, I sort of erased my two roots here. So it's pointing upward, and it goes down like this, and it comes immediately back up, and it's going to look something like this. Okay. Now, in order to get a more precise graph, I could figure out, well, what is the y value when the x value is negative 1? So if the x is, so this is step 3, plot some more points. If the x value is negative 1, it'd be negative 1 squared plus 5 times negative 1 plus 6. So it's 1 plus negative 5 plus 6. So it's negative 4 plus 6, which is, the y value would be positive 2. So when the x value is negative 1, the y value would be positive 2. So already I can see that my graph is getting a little bit off on the branches up here. So let's see, let me plot that point one more time. That also means that the line that I can get a point that's, so this one is to the right and up from the root. So if I go to the left and up from this root, I could find another point on this graph. Okay, so it's not very, it's hard because I'm not really zoomed in here. So these are, and the roots are so close together, but negative 1, 2. Okay, so it goes like, the graph would go something like this, and it looks a little strange, but it would go something like that. Okay, now I'm sort of limited by my resources because my graph is not, I can't really zoom in on it, but remember I found my vertex, there I can find my line of symmetry, then anytime I find a point in the right hand branch, I can use a line of symmetry to find the point in the left hand branch. Okay, now I'm just going to graph one more quadratic equation. So if I had something like this, now in order to find the roots here, I actually can't find them using the techniques in algebra that you have already learned. You're going to find techniques in algebra 2. You're going to use the quadratic formula in order to find the roots here, but I can't really find the roots using this. But I can put it in standard form. So if I put it in standard form, I'd have 1 plus 0x minus 3 is equal to y. So I can find the vertex here. Remember, the vertex is equal to, so the equation is x is equal to negative b over 2a. So that's 0 over 2 times 1. So that's 0 over 2, which is 0. So the vertex is 0 like this. Okay, so it passes through, well, let's figure out the y-coordinate. So if I put 0 in the above equation here, 0 minus 3, the y value would be negative 3. So my vertex is 0, negative 3. So I have 0, and then I'm going down to negative 3. That's my vertex. And I can still, if I put 1 in here for 1 in the equation here, I could get 1 squared, which is 1, minus 3, which is negative 2. So a point would be 1, negative 2. Okay, so 1 and negative 2 would be here. And so I know another point would be on this other side. So again, I could put 2 in there. If I put 2 in there, I'd get 1 back. So 2, 1, and in this manner I can, and I might want to get one more point, but here's how you can graph it. So I wasn't able to find the y-intercepts, although they have them. I just can't, they're not integer values. That's what I know. They're not integer values. You'll eventually find a way to do that, but I found the vertex, and then I found some points on the right hand branch, and I used the line of symmetry and reflection to find some points on the left hand branch. So there's lots of different things that you learned in this lesson today. You learned how to find a vertex, how to find the roots, how to graph using that information, and plotting a few values from the right hand branch to get the values in the left hand branch.